So far we've been counting things where the order of elements is not very important. For example, when we list the elements of a set, the set 1, 2, 3 is equal to the set 3, 1, 2, and we'd count those as both the same thing. However, there are plenty of times when the order of things is very important. For example, whether you come first in a race or third in a race is important, and it's also important to put your socks on before you put your shoes on. So in this section we're going to investigate the concept of a permutation, an arrangement of all or part of a set taking into account the order of the arrangement. Now it turns out that we can actually use the rule of products for all of our calculations in permutations. Just to recap, the rule of products says that if we have n operations and the number of operations is independent of the previous choices, then the n operations can be performed in p1 times p2 all the way to pn different ways. If this is sounding a little bit hazy, just go back and recap the previous section. So we're going to use the rule of products to solve the following question. How many different ways can we order the three elements of the set A, B, C without repetition? So here we're going to call things like A, B, C and A, C, B different. We want to count how many options we have for three orderings. And the way to think about this is to apply the rule of products and realize we have three things we need to do. So we have three operations to perform. The first thing we're going to do is pick the first element in the list. And if we think about that, we have three options there. So our P1 is equal to 3. The second thing we're going to do is we're going to pick the second element in our list. Now we'll have already picked one of the elements in our first operation, so we're only left with two elements that we've got to choose from. So our P2 is going to be equal to 2. And then finally our third operation is going to be to pick third in the list. And here in fact we don't have a choice because we'll have picked one element for our first option, another element for our second option, so we're just left with P3 is equal to 1. So our rule of products says that there are P1 times P2 times P3 possible ways of ordering these sets. So that gives us 3 times 2 times 1, which is 6. Now you could sketch this in a tree diagram. If we list our first operation, we have our three possibilities. We could either pick A as the first in the list, B as the first, or C as the first. And then once we've done that, if we're picked A for our first, then for the second we can either have B or C. On the other hand, if we picked B for the first, we could either have A or C, and if we picked C for the first, we can either have A or B. So now we've picked the first two elements, and that leaves us with no choice when it comes to picking the third. If we picked A and B for first and second respectively, then we have to pick C. If so far we've got AC, then we've got to have B. BA tells us that then we have to have C, BC and we have to have A, CA and we have to have B, and CB we have to have A. And if you follow each branch of the tree, then you'll see it leads to a distinct ordering of the letters ABC. So here we've got ABC, here we've got ACB, BAC, BCA, CAB, and CBA. And notice that we can see within this the way that we use the rule of products. So here is our first operation, was picking the first letter in our list. So this was operation 1. And then each of the subsequent branches, each of the second branches represents operation 2, depending on what we did in operation 1, but we still have two choices in each case, either B, C, A or C, or A or B. And then finally, we have our operation 3, and in each case, again, we have only one operation, which links to P3 being 1. And our net result is the 6 possibilities that we calculated using our rule of products. So it's a good idea to just spend some time working backwards and forwards, drawing yourself some tree diagrams and working with the rule of products, and make sure that you're comfortable with this reasoning. So just to point out, each of these orderings over here is called a permutation. And sometimes if we want to be specific, we'd say it's a permutation of the set A, B, C. So permutation means a specific ordering of the elements of a set. Now take a moment to just pause the video and use the same reasoning that we used in the previous problem to solve the following. We have 11 different items in my backpack, and if I take them all out and arrange them in a row, I want to know how many different arrangements are possible. So I'm not going to work through this, just take some time for you to pause, figure it out, and then I'll write down the answer. So what you should have found was that there were 11 times 10 times 9 times all the way down to 3 times 2 times 1 possibilities, and if you plug this into your calculator, you'd find that the number of arrangements is this long thing here. So we're going to take several of the things that we can notice from these two examples and draw some general conclusions. So firstly, in each of the preceding examples, we're asked to order or arrange elements from a single set. So we're not combining things from multiple sets, we've just got one set and we want to take the elements and order them. The next thing that we notice is that each element is listed exactly once in each arrangement. And this is, in fact, one way of defining a permutation. And since elements can't be reused, if there are n choices for the first position, then there must be n-1 choices for the second, n-2 for the third, and so on. The other thing that you might have noticed when we did the example with 15 things in the backpack is that the number of possible permutations grows rapidly as n increases. So we saw that when there were 3 choices, we only had 6 possible permutations, but with 15, it was a huge number. So what we'd like to do is take these ideas, which occur in many, many settings, and develop some notation to help us write things out usefully. So the first definition that we need is that of a factorial. So if n is a positive integer, so we're not including 0, we're counting from 1 upwards, then we define n factorial as the product of the first n positive integers. And the notation that we use is n factorial. So just to write that out, we have n factorial is equal to n times n-1 times n-2 all the way down to 3 times 2 times 1. This is the way it's traditionally written, but you could also think of it as 1 times 2 times 3 all the way up to n. So just so you can start to get a feel for factorials, One of the slightly odd things that we do is we define 0 factorial to be equal to 1. And while it's not immediately clear why we might do this, we'll see in a couple of lectures' time that it's the useful and sensible definition. Okay, so we define the 0 factorial to be 1. Obviously, 1 factorial is just going to be 1. 2 factorial is 1 times 2, so that's just 2. We've already seen that 3 factorial is 6, and you can carry on and check that these are correct. So it's a good idea to know the first 6 factorials just to save yourself time. So let's talk a little bit about working with factorials. A very useful rule is to note that n factorial can be rewritten as n minus 1 factorial times n. And this can be useful in simplifying. What do I mean? So we could try and figure out 4 factorial and know that it's 4 times 3 times 2 times 1. But we could also rewrite this as 4 times 3 factorial. And we already know that 3 factorial is 6. And so we know that 4 factorial is 24. We can use this idea to simplify more complicated things. Now suppose you need to simplify 25 factorial over 23 factorial. It's not really going to help to put this in your calculator because it's not going to be able to handle numbers that big. But we can rewrite things in a way that's helpful. So notice we can rewrite 25 factorial as 25 times 24 times 23 factorial. And we're going to divide that by 23 factorial, and you'll see that now we can cancel our 23 factorials, and we're just left with 25 times 24. And that you could certainly put in your calculator, but leaving it like that is just fine. So here's a more general situation. We want to simplify n plus 1 factorial over n minus 1. Well, we're going to use the same trick. We can write n plus 1 factorial as n plus 1 times n times n minus 1 factorial, and divide through by n minus 1 factorial, and again we can cancel, and we're just left with n plus 1 times n, and you could write that as n squared plus n if you wanted to. So these are ways that you can use this useful fact to work with factorials so that you don't have to plug them into your calculator. So just to kind of reiterate what I said, n factorial grows very quickly as n increases. For example, 11 factorial is 39,916,800. And as soon as you go higher than that, your calculator's not really going to be able to handle it. So you don't need to calculate and write out factorials bigger than about 6 factorial. Just leave them in factorial form. If we think about summarizing what we've seen in the examples earlier, we can use the following rule. If we have a finite set of size n, then there are n factorial ways of permuting or arranging the elements of A. So if we're thinking about putting A in a specific order, there are n factorial ways of doing that. But we can now think about a more general situation, and we're going to start with an example. Suppose we have a club with 25 members, and it's holding an election for president, secretary, and treasurer in that order. We're going to assume the person can only hold one position. We'd like to know how many ways there are that we could choose the 3 officers. So again, we can use the rule of products, which says, okay, we have 3 things that we're doing. So we have 3 options that we have to choose from. We're choosing the president and the secretary and the treasurer. And so off we go. We think about how many options there are for president. Well, there are 25 options. And then one person out of the 25 is going to be the president. So when they come to pick the secretary, we've only got 24 options. And then by the time we pick the treasurer, we've already had 2 people picked, so there are only 23 options for what we can pick. So our solution is going to be 25 times 24 times 23 by the rule of products. So now we can actually give a formal definition of a permutation. A permutation is an ordered arrangement of k elements selected from a set of n elements where k lies between 0 and n, where no two elements of the arrangement are the same, and this is a permutation. And it's called a permutation of n objects taken k at a time. And we denote the number of such permutations by this here, p n k. So things to be aware of in this definition is that no two elements of the arrangement are the same, so we're not allowing duplicates. And now, if we want to calculate the number of permutations, you can use the rule of products, but we can also use what's called the permutation counting formula. So the number of possible permutations of k less than n elements taken from n elements is, and you should be able to see where this comes from looking at our previous example, it's n times n minus 1 times n minus 2 all the way to n minus k plus 1. And it turns out that another way of writing that is n factorial divided by n minus k factorial. And it would be a good thing for you to check to actually write this out. So just check this, using the tricks that we used previously. There's some other notation that sometimes gets used. If you've seen summation notation, this big pi is acting as a product, and it's just saying add together products of the form n minus j, where j goes from 0 to k minus 1. But we're not going to use that very much. Mostly we'll use this form over here. So let's use this to figure out another example. So we're actually going to do this in two ways so that you can see that using the rule of products works just as well. So let's check. So we've got a club has 8 members eligible to serve as president, vice president, and treasurer. How many ways are there of choosing these offices? So let's use the rule of products. Okay, so we're choosing a president, vice president, and a treasurer. So we have 3 operations that we need to take care of. So this is choosing the president, choosing the vice president, and choosing the treasurer. Now the president presumably gets chosen first. So there are 8 ways of choosing the president, and assuming that we aren't allowed to have someone acting as president and vice president, when we come to pick the vice president, we get 7, and if we get the treasurer, we've got 6. So that's using the rule of products. And now let's see, can we use the permutation computation rule? Well, let's just go back and have a quick check. We've got an ordered arrangement, so we need that, of k elements, so for us that will be 3. Selected from a set of n, our n will be 8, where no 2 elements of the arrangement are the same. Well, so long as we can't have someone acting in 2 roles, that's true. So it looks like we can use the permutation counting formula. So I'm going to use it in this form over here. So we want P of 8 objects choosing 3 at a time. So that's going to be 8 factorial divided by 8 minus 3 factorial, which is 8 factorial over 5 factorial, and I'm going to use my simplification here. 8 factorial is 8 times 7 times 6 times 5 factorial divided by 5 factorial, and so that's equal to 8 times 7 times 6. And notice, delightfully, we've got the same answer. So this certainly seems to work. So a good idea now would be for you to go and look through example 2.2.3 in the textbook and see if you can solve it in the two ways we've just done. So firstly using the rule of products, and then using the permutation counting formula. It's important to be able to use both of these because it's going to turn out that there are times when you can use the rule of products when you can't use the permutation counting formula. So having said that, let's look at a few examples. What is important to realize with combinatoric type problems is that you need to read the question really carefully and decide which counting rules apply. So here we've got an example from the textbook. We're ordering digits under different conditions. So we're considering just the digits 1, 2, 3, 4, 5. And the first thing we're going to do is say how many 3-digit numbers can be formed if no repetition of the digits can form. So for part A, we look at this and we say, well, we could do this using the rule of products. Because we have 3 operations, and in each case, the number of opportunities in each operation is the same. So we could say, okay, choosing the first, second, and third number, we have 5 opportunities for the first, 4 for the second, and 3 for the third. Or our permutation counting formula. And the reason we can use this is because we're picking things from one set and we're not allowing any repetition of digits. So if we use permutation counting, we're going to have P of 5 choose 3, which is going to give us 5 factorial, 2 factorial, and again if you simplify this, this is 5 times 4 times 3 times 2 factorial over 2 factorial, so our two answers are the same. So either of those methods work for part A. But if we look at part B, now suppose we are allowed repetition of digits. Well, we can still use the rule of product. We have 3 operations. We want to choose 1, 2, 3 digits. Picking the first digit, we have 5 options. Since we are allowed repetitions, in fact we have 5 options for the second digit and 5 options for the third digit. But we can't use the permutation counting rule because of this repetition that's allowed. And remember, if we go back and have a look at our definition of a permutation, no 2 elements are allowed to be the same. So we can't use that here. Oops. Now let's have a look at part C. How many 3-digit numbers can be formed if only non-consecutive repetition of digits are allowed? So let's think about what non-consecutive repetition means. So non-consecutive means one thing following another. So for example, we're saying you can't have 5, 5, 4. That's not allowed. But you could have 5, 4, 5 because at no point you could have that because at no point do you have 2 of the same numbers next to each other. So now let's think about that. If we use the rule of product, again we have our 3 operations, and let's think about how many options we have for each one. Well, we have 5 ways of picking the first thing, and then we're not allowed to duplicate that number again, so we've only got 4 for the second one. And then if we think about what's happening for the third one, we will have picked one number for the second one, and so there are 4 other things that we can pick so that we don't get a duplicate. So we get 5 times 4 times 4. And again, we can't use the permutation counting formula because we've got repetition. So it's worthwhile to spend some time going through these examples, and more examples at the end of the section, just to make sure that you are happy knowing when to use the rule of product, when to use the permutation counting rule.